All right, folks. So topic of today is generative adversarial networks. I suppose you can see these two cats don't look very friendly with each other. Right? So what are GANs? This topic is so, like when it came out in 2014. And it completely shook the machine learning world. Jan LeCun, the head of AI research at Meta, he went on to say, adversarial training is the coolest thing since sliced bread. This is not anybody. This is one of the great luminaries and a Turing Award winner, standing next to Hinton and so forth. And he called this algorithm or this neural architecture that we do so radical. Many people believed that this algorithm may be the first true AI, they called it. And some believe that it was the first true AI algorithm in some sense, in the sense that whatever their notion of AI was in those days, they thought it was. And it represents a very interesting and remarkable departure from your standard feed-forward network, CNNs, etc. And what you could do, it uses that, but the way it uses that is very, very clever. So I hope you will pay attention to this session that we're going to go into. But I will explain that, and then we'll play some games, visual games, and we'll make progress. Now, by the way, I must also mention, guys, that in the paucity of time, because this course is so fast-paced, and we have to do so many neural architectures together, during the session, I'm not walking through the code, Jupyter notebooks. These notebooks, however, I will be uploading to the course portal, and through the summer, I'll do small walkthroughs. There'll be sort of a long tail in which optionally you guys can attend, and we'll do a lot of code walkthrough and little code exercises. It will be all preparing you to what comes next in the bootcamp. So anyway, some resources. You have, GAN is a big, big topic. If you look at just the number of GANs that are available, basic theory of GANs, do you realize that there are all sorts of things? Flow GANs, dueling GANs, CRNN GANs, like causal GANs, DC GANs, right? And we did VQVA. There's a GAN version of that also, VQ GAN, very, very powerful. So the world of GAN is extremely rich. Generative adversarial networks is extremely rich. A lot of work continues to be done in GAN. And you just look at the sheer amount of research papers, and these are only the important ones, the best
Asif?
ones. Yes.
Are GANs used in agents? I mean, some of these agents are collaborative and adversarial, right? So just curious.
They could be used. Agentic reasoning typically is for critique. You could do an adversarial game between agents, but I haven't seen any research paper that does it in a very effective way at this moment. But it may be my blind spot. But a very good question, actually. I don't know. Generally, you don't think of it like that. So that is that. We will deal with that. The original paper of GAN, this is by Ian Goodfellow. So I'll tell you how this thing came out. By the way, one of the authors of this landmark paper happens to be my cousin. Oh, yeah. So the story of this generative adversarial network is like this. Ian Goodfellow apparently was in the pub, in a restaurant, bar, and he was a little inebriated. Some people get some of their best ideas when they loosen up a little bit. Right? And so he started having the kind of crazy idea that normally sane people wouldn't have if all their faculties are intact. And he became quite persuaded that it would work. Good, I suppose, that he was a bit drunk, because his better reasoning may have told him, don't do it. He apparently went back that same night, started coding it, and a very preliminary version, he made it work that very night itself. It was very preliminary, but it did prove the point that it can happen. And to think that what these guys created, and he principally created, I suppose, was called later on by Jan LeCun as perhaps the coolest thing since sliced bread. Many people called it the most, like almost like a next level of AI when it came. And it really did feel it. It also took the generative part of the AI, it put it on steroids. It really did a huge advancement to that. So now the question is, I hope that gets you sufficiently interested in knowing about it. Are you guys interested? So let's go and do that. What it is, and I'll go into the writing mode to explain this paper. Generative, the word is generative. Adversarial network. Right. So let's read it backward. Network. Well, we are talking about neural networks. So that part is easy. Adversarial needs explaining. And this comes a little bit from game theory, and I'll explain that. And generative, so I'll just talk a little bit like this. See, in machine learning, there are two kinds of models. One is discriminative, there's one categorization, versus generative. So would somebody like to enlighten me? What's the distinction between discriminative?
Is classification. It is trying to figure out what is the difference between different images, like cat,
right.
dogs, for example. The generative is like pull the rabbit out of the hunt.
That's a very descriptive way. Somebody said, here, Prasanna said, that discriminative, an example is classification. They're telling, is it a cat or not? Right? And generative is literally coming out with something, pulling a rabbit out of your hat. Right? Pulling a rabbit out of your hat. That's a very colorful way of putting it, and I'll stick to, let's take that. Right? More strict mathematical definition would be that in discriminative, you're saying given the data, input X, right? What exactly is this? Which class is it? Right? In other words, cat or dog. What is it? Right? So you're saying, what is the probability that it's a cat given the input? What's the probability that it's a dog? Which probability is more? That's the sort of question you're asking. Or you're asking, given this, what is the y hat? Given the input, what is the value of the output? Like, for example, how much ice cream is the young entrepreneur likely to sell today on the beach? Right? So these are tasks that are discriminative. What the generative, but then what about generative? So pay attention to this equation. Suppose you knew the entire distribution of the data, the joint distribution of the input and output. Right? So for example, if you could tell that in the landscape of, let's take one-dimensional input and one-dimensional output, right? Suppose you knew this is it. This is how the probability distribution of the data is. That what does it mean in real terms? That these points are much more likely. You see that, right? In the plane, these points are much more likely, right? On the other hand, this point is unlikely. Why? Because the probability of that joint probability of that point is close to 0. Does that make sense, guys? And so what can you do with such a model? Oh, if I know the real probability distribution of the data, we have just come from the land of VQ, variational autoencoder. What did we learn there? If you know the real probability distribution, you can go on generating. You can go on generating realistic outputs and inputs. Does that make sense? Right? So knowing the lesson is knowing the whole distribution, knowing, and guys, this is one of the amazing things about math. You realize that just as you wouldn't have thought much. One is a conditional, this is a conditional probability, and this is a complete probability. Complete probability. Probability. Right? The amazing thing is knowing this entire thing makes it, leads to, or gives you, knowing this gives you a generative model. And if you think about it, like you go like, wow, that's all it is. Because if I can really know the whole distribution, I can generate lots of
questions. When we say we really know the full distribution on whatever training data we get, right? Okay.
Yeah. So you give me a lot of training data, input, output, and if I could learn the whole distribution, wow, I could simulate, I could create lots
how do I know that? Sorry to interrupt again. How do you know that I have I have the full distribution? How do I know that?
Take a huge set of XY pairs. You take a huge, and then you hope and pray that you have some algorithm to create this whole distribution. Now, the problem with this is, like, and you came to that, see, this complete distribution is hard because you need to know, amongst other things, for example, this can be broken up into two ways. Probability of y given x times probability of x. So you need to know the input data distribution. You need to know the conditioning of y.
Yeah.
Given x, what is y? Right? Whereas this here is basically given x, what is y? Right? It is a much smaller part of the problem. So generative needs to know a lot more. It needs to know this part as well as it needs to know this part. Right? So in machine learning, and of course you can write it the other way around. You could write, well, anyway, I'll leave it like that. This part is your discriminative part, somewhat similar to this, but you still have to know the actual distribution of the data itself, which is not at all easy.
Yeah.
Right. And so historically, and by the way, forgive me for this mathematical digression. If you don't get it, doesn't matter. The simple thing to remember is look at this picture, and you know that if I know that points are much more likely here, all I need to do is pick a point in that region, and quite likely, it looks realistic. People wouldn't know whether such a thing actually in some data set it exists, such a point, or you just cooked it up. Right? That's what makes it generative. Yeah. Generative but generative has always been much harder than discriminative models. This is true, by the way, even today. We talk about generative AI, and quite often when people talk about it, when you hear laymen talk about it, they breezily talk big words, generative AI, LLMs, etc., and they mix the two up. But actually, generative is anything that can, in some sense, have a sense of the distribution, the whole distribution, or it can produce data that is realistic. You see, when you ask a question to a LLM, it answers you. That answer doesn't exist in a data set. It's a unique thing, but it looks very plausible, isn't it? LLMs are, in many ways, a plausibility engine. Yeah. But they're not the they're not the only generative model. Generative models have been there for a long time. Right? For example, naive Bayes, one of the classical algorithms, it's been there for decades. But anyway, leaving that aside, let's come to this fact. Even today, every generative model, let it generate something. And then you ask, is it good? Is there a problem with it? Ask a LLM. What's the, let's say, what is the answer to this question? It will answer it. But then to the same LLM, you ask a different question. Do you think this answer is correct? And then it may say, no, I don't think it's correct. You see that, right? So even LLMs, they are much stronger critics. They're much better at discrimination than they are at generation. Because discrimination is an easier problem. Generation is the harder problem. So one of the things you learn when you do the bootcamp is we'll create this, and these days, the biggest topic of 2024 is AI agents and agentic reasoning. And one of the things you'll always do, one of the best practices is planning, etc., but critique. You will have a LLM show its thoughts, produce something, but you'll always keep a critique, the same LLM as a different agent, behaving as a critique and criticizing its own work. It's a very effective way to make sure that you get good quality results. But that's for another day. Go ahead.
Some relate this to this, the evaluation and owners. So does it end up using it or it's a
No, this is a completely different architecture.
okay?
Well, there is it is a different architecture. There are places where they meet, there are places where they are different. It's like broccoli and potatoes, right?
Okay. So,
There are times you put broccoli and potato in the same dish. Quite often you don't, but they're different.
they are substitutes.
They do have overlapping functionality. Right? In fact, you'll realize that GANs do a lot of the generative tasks, quite a few, not all, much better than autoencoders. Right? And that's a point. That's why when they came onto the scene, they were quite a remarkable breakthrough, really amazingly. So here is a thought that you have to ask. And this is what people were thinking. I suppose this is what, how did I know that Ian Goodfellow was thinking like that? Either from an interview of his I must have heard, or from somewhere, I forget how. So I know that the basic question that these researchers and Ian were asking is this. Right? And so I heard that, see, discriminative models, a classifier, discriminative models are great. We are talking about circa 2014. If you go back and look what happened around that time in neural networks, AlexNet was already there, ResNet was on the scene or about to come onto the scene, right around the corner, right? What were they doing to ImageNet? They were crushing the benchmarks. MNIST, they were crushing the benchmarks, isn't it? They made it so easy, those CNNs, that after a little while, it almost looked foolish to give it a problem so easy as the MNIST dataset, the handwriting recognition problem. Those were big breakthroughs in 2012, 2014. And those were defining moments. If you remember, before 2012, people were not even taking neural networks seriously. Just as a bit of history from one of the talks that Jeffrey Hinton gave, he said that if you would submit a paper in computer vision and mention the word neural network, they would actually reject it. And not just him, all other researchers. You couldn't, in computer vision, you couldn't use the word neural networks. Right. Today, it seems unbelievable that the situation was like that. But we are not talking of things in the ancient past. We are talking of things just 10, 12 years ago. And so when then Fifi Lee was creating the ImageNet dataset here at Stanford. She was actually told that she won't get a tenured position at Stanford. She won't get a faculty position, sort of confirmed, if all she works on is gathering images from the internet and creating the largest collection of images. Right? That's how people used to think. Today, you can't believe it. Obviously, Fifi Lee commands tremendous respect today. But then Hinton and his colleagues came to know about the ImageNet problem. They were looking to prove that it works, right? They think works. And they were already seeing good results with MNIST, and so they applied it to the ImageNet also. When they sent the paper apparently to be reviewed, there's a bit of sort of a back history. You see the human dimension. They actually went to the person and asked, let's see, the benchmark, whoever was the authority on the benchmarks. He says that, see, are you willing to believe that the ImageNet dataset is a legitimate benchmark? They didn't say he didn't talk at all about his neural network. Okay? And once the authority, I forget the name, said, all right, yes, ImageNet is real and a good algorithm would be, it can be used to measure a good algorithm. Once that was stipulated, then Jeffrey and friends wrote that whole, I think it was AlexNet, they came out with that paper, which just crushed the AlexNet benchmark very well, right? It did very well, and it was already crushing the MNIST. It didn't crush ImageNet, but it made a huge advancement, unprecedented advancement. And that is when the paper got accepted and the world woke up that there is a new way to do computer vision. So do you realize that all of these things were just happening at that time, 2012? And it seems hard to believe. Well, by the way, I myself came from a computer vision background. I did my computer vision in the late 90s. And I do recall that there was very scant, if any, mention of neural networks in computer vision. I took a different course to do analytics, which is the machine learning course, but not computer vision course, right, in the 90s. So that was the world, and how much the world has changed. So around 2014, people like Jan Goodfellow, they were looking at it and saying, look at this discriminative models. Discriminative models are great. They're crushing the benchmarks, right? They're proving so effective. They can tell this is a truck and that's a cat and that's a dog in vast data sets, right? With CNNs, they were doing that. But the generative models were in a rather sorry state. There wasn't much of it going around. The autoencoders were still coming out, but variational, actually, if I remember right, it came after. It wasn't even there, right? Variational came in, if my chronology is right, variationals were discovered after the GAN was discovered. One of you can please confirm that. Right? I was checking the history. When did the first variational paper came out? I believe it was 2015. GAN came out in 2014. Look it up, or correct me if I'm wrong. So anyway, generatives were in a pretty sorry state. There wasn't much. So they asked this question, which is brilliant, right? I suppose you need to be a little bit less critical or thinking. And they asked this question that, see, and I'll give you a physical analogy. See, if you want to learn tennis or be good at tennis, how do you become good at tennis? Do you play against a really weak tennis player, or would you play against a player who's better than you?
Better.
Come again? Better, right? Better. Because the other person challenges you, pulls you up, isn't it? You have a way to know, actual way to measure that you're improving. Whereas if you play against a weaker player, there is no way for you to know that you're doing better, isn't it? Likewise for chess, likewise for anything, right? How do we stretch our minds in school? Every grade, you master the 7th grade. By the time you're done with 7th grade, everything in the 7th grade school books begins to look easy. Then they put you in the 8th grade. It's a little harder. books look a bit harder, right? So you have to stretch your mind to grasp the books of the 8th grade, let's say. This is a common human experience. So they leverage that. And
came compared to but VA is
say that again.
later. Right?
MNIST has been there since the 90s, 80s, 90s. The ImageNet came later. ImageNet pretty much coincided 2012. Big data movement got the ImageNet. Okay, so guys, there is a game theoretic thing. It's called an adversarial or zero-sum game. Example of zero-sum game is tennis. I win, you lose. Isn't it? Chess. These are zero-sum games. Right? A cooperative game is the other way around. Right? What's an example of a cooperative game? Two kids sitting on the beach together. One brings the sand, another brings the sticks, and they go about making a castle. The goal is they make a beautiful castle. Right? So that's a cooperative game towards a common goal. That's a win-win. Right? Looking for win-wins. Adversarial games or zero-sum games are where there's no way one can win without the other losing. Right? And tennis and all of these things fall into that category. So those are adversarial games. So the key insight that Goodfellow et al. Had was, what if we could do this? We don't have a really good generative model for images, right? Or for data or for anything. But let's do this. Let's play a cop and counterfeiter game. Right? What is so I'll just reframe it in a sort of with an analogy so that this game makes sense. Let's say that you have a cop here, and you cop, some currency comes through. So here's a dollar bill, right? Here's a US dollar bill. That's how it looks, more or less, simplified, right? And the cop should say, okay. And then suppose you decided that you are Neil Caffrey in White Collar. Anyone of you remember what this TV show is, Neil Caffrey? Neil Caffrey in White Collar? No. Okay, I won't make TV show illusions. It's a very popular TV show that used to be based actually on the life of a real person. So there's a little bit of a side. Anyway, do you want to hear the story? There was really a young kid who was a brilliant person with a very tough life. And what he used to do is he would, like, for example, knew how to counterfeit currency or bonds and so forth. And then sometimes he would impersonate a pilot, literally a commercial airline pilot.
You can catch me.
Yeah, Catch Me If You Can. Exactly. There was a movie built on his life. Catch Me If You Can. That person is real, actually. He gave a talk. He's there in FBI, and he gave a talk at Google.
Yeah.
He's old now. Right? Leonardo something. Okay. So something like that. So imagine that you're a great counterfeiter, but you haven't seen the currencies of US. You need to somehow fool the cop because you need to buy food or whatever. So you create a currency, right? And in the currency, you think that US currencies, everybody loves elephants. So there must be an elephant on the currency. And you try to pass it off. What will the cop do? It will say, well, get lost. This is not a dollar bill. Does it make sense? And it will say, no, this is not a dollar bill. Am I making sense, guys? Yes. Right? Now, here's the rule of the game. The cop and let me just call this the counterfeiter. Counterfeiter, right, or the faker, will produce a bill. What is his goal? The guy who makes counterfeits, what's his goal? To make it as realistic as possible, isn't it? So now, In terms of the machine learning that we have been talking the last few weeks, what does this really mean? Hint, hint, distribution, probability distribution.
Concept of
See, if this all the real currencies, they're all the pixels. So, you render it as pixels or some data, a vector. You have an input vector, X, right? X will have some probability distribution. Right? It will look something like, right? It will have a shape like this. Let us say that this is the shape of the distribution, P of X. If it were one dimension, obviously it's not. Let's say that it had a shape like this. Are we making sense? Then this person comes and produces X prime. When will he start producing X primes that will fool the cop? When he has discovered this probability distribution. If he discovers the probability distribution of the real data, what does that mean? X is real. This is fake. X prime is fake. The only way the counterfeiter can figure out or start being successful at passing bad bills as dollar bills is if he has somehow figured out what exactly does a dollar bill look like, isn't it? In detail. Are we making sense? It's as simple as that. Now,
he hasn't seen that sample.
He's not seen the sample. And that's the thing. All he can know, he doesn't know. He'll never be told what a dollar bill looks like. All he'll be told is whether the cop caught it. Are we together? So let us say,
but possibility is more, right? Easily rejected.
Yeah, in the beginning, he'll produce some junk. He won't. So, for example, he may just believe that it is made up of stars. Obviously, this will be rejected, isn't it? So the generator will turn out hopeless in the beginning, let's say, if the cop was already clever, right? But here is a game we'll play. What we will do is we will take a completely dumb cop who has never seen dollar bills, right? And we will take a counterfeiter who has never seen dollar bills either, right? But, and here's the best part we'll do. We'll make them play adversarial games, right? If the cop gets the prediction, and what we will do is to the cop, we'll give either the real dollar bill or a counterfeit produced by the counterfeit. Are we together? Randomly. At one time, you give it the dollar bill, him the dollar bill, or you give it the counterfeit. And if the cop gets it right, it's okay. But if the cop gets it wrong, there's a penalty, there's a loss. Are we together? So what are the possible outcomes that you can have? Now, let me, by the way, guys, math, as I said, is common sense read with just less words. So the output can be either real. The real answer is, the reality is either it's a real bill or it's a fake bill, isn't it? So now let's look at the cop. Suppose the cop predicts for a real bill, the probability is high, close to 1. Then the loss is low. You don't want to penalize it. But if the probability that the cop comes out for the real data, right? So X is, like you say, sampled of real data. X is an instance of the real data, sampled from the real dollar bill. But if the cop says, no, very low chance that this is real, probably fake. What do you want to do? The cop is making a mistake, isn't it? Would you agree? Right? And so you need to quantify the loss with log, because what is log of 0? Log of 1 is? Log of 1 is 0, no loss. log of very small quantity, 10 to the minus 5 is minus 5, isn't it? So, and the negative of that will, of course, be a big loss. 5, for example, if you're looking into powers of 10, like log of base 10, something like that. Are we making sense? Right? So for the COP, for real data, this is one term for the loss, but the COP also not only should. So one easy thing the COP can do is, for every data piece, he can say real, 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 real. He'll become very good at telling that, spotting the real. But has he actually learned something? It's a useless COP, isn't it? A COP that says all bills are real will certainly be able to, it will look as though he can spot the real, but he's useless because he's calling everything real. So in the loss term, you also want to add a term that says, if you get the data from, let's say that the generated data, fake, x prime, probability of x prime should be, it should be, what should it be? Low, right? It should be as small as possible. In other words, 1 minus this probability should be high. Like he should say, if you encounter a fake, x prime is fake, x prime is sampled from fake data that the counterfeiter gave, you want the COP to say probability of its being real is, P is the probability of real. P will just define it as probability of real as the COP perceives it, as the COP perceives. So a good COP should give very low probability to fake. Would you agree, guys? Is it looking common sense? And therefore, 1 minus P is the loss. Because if this user gives a high probability to this, 1 minus P will be low. And so the other loss term would be this. Am I making sense, guys? Right? So the COP has to, the role of the COP is, this first term, identify real as real. And this term helps you identify fake as fake. Am I making sense, guys? Isn't it? And so you would say that what you really want is the net loss function. Guys, I hope I'm talking complete common sense here. Am I? Is there any confusion? Right? So the loss function for the COP should be, well, again, log P of x when x is taken from, sampled from real, minus log 1 minus P x prime. X prime is sampled from fake. Fake that the counterfeiter produces. When counterfeiter gives, you need to give a small answer. Probability of real is low. The COP says, I'm really suspicious of this. A good COP will be able to do that. Isn't it, guys? So what you need to do is, any deviation from that is an error. It's a measure of the error. Guys, tell me that so far so good. Right? Now, what about the counterfeiter? For the counterfeiter, let me just use the word crook, because I don't want to keep writing counterfeiter over and over again. Now, what about the crook? Crook wants to fool the COP. Remember, what is the goal of the crook? Somehow fool the COP. So what he wants to do is, he wants to generate, see, he will generate somehow based on something. Let's say that what he will do is, he'll randomly take some paper, right? And then massage it, paint it, do whatever he wants to do with it, and produce an X prime. Something he generates. All right, guys, right? So crook generator function. So he has figured out why is this important? Crook has some mental picture of what reality looks like. Isn't it, guys? He'll have some mental picture. And that mental picture he will have in a function G and says, okay, if I use that technique, right, then here is a fake, a good fake. I'll produce. So far, so good, guys. But if it is a good fake, then ultimately the cop is going to look at it. Let's say that the cop produces the probability, right? What will it do? The probability from the cop, as the cop sees it, of X prime is the same as probability of the cop seeing G of the fake, right? Are we together? And what will the crook want to do? Crook wants to produce as good, wants to maximize the probability of real that the cop perceives. Does that make sense? Right. So now, isn't it common sense? The crook will say, oh shucks, I created this work of art and it was immediately caught by the cop. Let me change it. Let me repaint it a little bit. Try my luck again. And so now you can keep playing the game. What is happening is the cop has a bit of an advantage because the cop is at least told when his answer for real is wrong. He's also told when his answer for fake is wrong. Both the things. Remember, the cop gets two answers, right? For real and for fake, both. You tell it in the as a supervised learning exercise. It's simple classification problem. You tell it, oops, that was fake. Oops, oh no, that was real, right? So the cop learns from both real and fake because in the back propagation, we learn from that. But the interesting thing is the crook has never ever seen a dollar bill. Isn't it amazing? Now, do you think the crook can ever catch up? What do you think, guys? Do you think that crook can ever produce a dollar bill that looks realistic?
Yes, I think so.
Yes.
All the time.
Gradually you would. But here's the thing. Usually counterfeiters or crooks, they know what a dollar bill looks like. But in this particular adversarial game, crook is never shown a dollar bill, is never shown the real data. So what happens is, or more precisely speaking, let's say that this is the actual distribution of the data. The crook essentially has to somehow figure it out from the backprop of gradients of the crook loss function. Isn't it? All that the crook is told, goodness, the cop was pretty sure you're fake. So now what will the crook do? It will say, well, you know what? If he was very sure with this elephant, let me make it look a little less like an elephant, right? Maybe that will help. Are you getting the point, right? And keep on trying and keep on trying. And the hope is soon the crook will figure out that the dollar bill has the Benjamin. Who actually dollar bill has Lincoln or who? What does it have? George Washington. Okay, Washington on it, right? So it will be able to, without ever having seen a dollar bill, it will just make small changes and see, is it able to confuse the cop or not? Is the cop less sure? The cop may still be 99% sure, but next time, maybe the cop is only 98.5% sure, something like that. You know? So you'll keep on making lots of modifications. And so what will happen is, and now let's use the formalism, you say the cop is the discriminator. Why? Whatever input it gets, it applies a discriminative function to produce what? The probability of its being right or wrong. So D of X is essentially what we wrote as probability, P of X, isn't it? All the D of X, the discriminator in this vocabulary, you use not P, but this D, discriminator. I'm sure somehow I feel I've misspelled it. Okay, but that is it. Let's just call it COP. COP needs to produce, the COP has a discriminator function, a test with which the COP determines whether it looks real or not. The COP has some mental picture of what a real dollar bill looks like. Remember, even the COP starts out not knowing what a dollar bill looks like, isn't it? And so it produces a y hat, a probability that it is, right? Now, what you do to the way you train it is you take lots of real data, think real dollar bills, and then you have a generator, right? What the generator will do is it will just take a point sampled of, let us say, some form of noise. Let's take a normal Gaussian distribution, right? In whatever dimension. Z can belong to, you can pick your dimension, 1, 2, 3, 4, whatever it is, some D dimension. What does it need to do? Let's say that X belongs to n dimensions. Real data belongs to n dimensions. The output of this has to be minimally, for it to be sensible, it has to be, X prime also has to belong to n dimensions. Does that make sense? And now the way you train the network is you don't tell the discriminator what you're doing. Randomly, either give a real or give a fake. But it is labeled data. You know whether it was real or fake, isn't it? And so what will happen is the cop will start getting smarter because it is being told this was real, this was not real. And what about the crook? The crook will know that the cop was very sure what you gave it was fake. But the crook will now make a small alteration to it and then try the luck out and say, aha, that seems to have slightly, it seems to have created a confusion for the cop, right? Because what you want, the crook wants, is that his dollar bill looks just as good as a shiny new dollar bill, real dollar bill. Albert.
So how do you know? Because there are infinity combinations. So you are going from all kind of things to George Washington's face, for example.
Right.
So how would you go through is it through the loss function?
That is it. That's the magical thing about neural networks, that the unreasonable effectiveness of mathematics, the fact that the loss function can teach you, can just nudge the crook slightly in the right direction and also make the cop smarter. So what happens is, like, the cop and the crook, they both act to smarten each other up, isn't it? Do you see that? Because suppose the crook becomes very good and the cop hasn't caught up. What does that mean? Now cop will start having rather large loss function values, discriminative loss, and those gradients will back propagate and it will pull the cop up, right? On the other hand, let's say that the cop is very smart, quite smart. Now, well, what happens is, if you make the cop too smart, actually in reality, practical reality is that it becomes a little bit harder for the crook to catch it. But let's say that it is just a slightly bit smarter, then it gives a leeway for the crook to learn, because the crook is producing something, but the cop is rejecting it, it's getting a loss. So it has enough incentivization to change its art. Are you making sense? And so what will happen is that eventually they will reach an equilibrium situation. Just as you guys, if two people keep playing tennis, what happens? They both become very good at the end of it, right? So it's a min-max game. One is trying to minimize the separation between, or the ability to tell the real from the fake. Who is trying to minimize? The crook, isn't it? The generator would rather generate such a good fake that it looks real. And what is the discriminator trying to do? The cop trying to do? They're trying to learn subtle signals that will help it maximally tell apart a fake from the real.
So ask it both are neural networks here.
Both are neural networks. So this is the min-max game. So they are playing what is called a min-max game. Are we together, guys?
Competition between the generator and the
discriminator. Right? Now comes the interesting thing. Generator generates it out of what? If it is a neural network, it needs an input, isn't it? And the answer to that is just sample off noise and give it to the generator and let the generator, and this is the most odd thing that takes a while to come to terms with. What did the generator generate? Because if you create a neural network, so many layers or whatever it is, CNN or whatever, at the end of it, you have to give it something so that it will transmute that something into a fake. But the interesting thing is you can just sample it off some noise and just say, hey, here is noise. Just go transform this noise, this random noise, into a realistic looking counterfeit. It's like you're giving a counterfeiter, a great counterfeiter, just clay. And the counterfeiter is shaping that clay into a very realistic statue. That's it.
So is this become a denoising for denoising alternate
It's
code?
not denoising. It doesn't, because there is no signal there at all. Denoising comes in when you talk about a mixture of information and noise. Then you can say I can denoise and increase the information to noisation. But here you're starting with 100% noise, and you're saying take noise and somehow transmute it into a signal, into a beautiful fake, right? Into a good counterfeit. And it almost looks unbelievable that you can do it, right? It's a min-max game, and this is
asking
it.
one question, sorry. So do the generator or the bad guy gets any feedback, from the cop saying that it's not good, but any such feedback so that the
The generator doesn't get a feedback from the cop, but gets a feedback straight from the loss. See what happens. Cop, you produce. So think about it this way, Krishna. You start the generator produces this, right? Generator produces this. This goes into the discriminator. Discriminator, suppose it produces a value and says 0.3.
okay.
The cop is pretty sure it's not real, isn't it? So there is a loss. You can take the gradient of the loss, and you can now backpropagate it and update the generator.
Okay, so I was talking only that. So the generator, the loss will be used as a feedback for generator, right?
Exactly. That is why. And so let us now go back and see how what the obvious loss terms I wrote. What did I say? As far as the crook is concerned, the loss function of the crook is, let's say, the crook generates something, G of Z, the noise. So what is it? This is X prime, right? X prime is equal to this, right? It produces this. This the discriminator acts upon, right? And produces a probability, some probability that it's real. When suppose the discriminator comes up with a very low number of it being real, oh boy, you're in trouble, isn't it? What you really want to have is that the discriminator should not be able to tell that this is fake, right? That this is fake. Let's say that real is 1, fake is 0. You want this answer to be discriminator. You want the discriminator to be as close to 1 as possible, isn't it? So predict that it is real. Are you getting that, Krishnan? You would rather, as a crook, want the discriminator to produce a number. So in other words, if it is less than 1, that is 1 minus that, this is a measure of how imperfectly you're generating the fake, right? Your faking is not perfect yet. Counterfeit is not perfect yet.
Yeah.
You need to improve upon it. And so the and this is something that you have to remember, that you are trying to maximize this. You're just trying to maximize this as a crook. The cop has to do double duty, right? The loss, now from this, the loss function you can create, your same cross entropy loss, all of that you're familiar with, how to make a cross entropy loss out of it, negative log likelihood and all of that. What about the cop? Cop has a double duty. The generator never sees, the crook never sees a real dollar bill. He has no relationship to real data. Just has to imagine it out or figure it out. The cop, on the other hand, is given either a real data or a fake data, right? And has to get the answers right on both cases. So the cop has 2 terms in his loss function. Right? Means real must be real, real's probability must be high, fake's probability must be low. Does it make sense? That is it. So that's the min-max game. And a min-max, a two-player min-max game has been an effective strategy. And it really works when, let's say, see, what happened is that if you go back and look at the time this generative adversarial networks came out, as I said, discriminators were doing very well. And so what is the key insight or idea that Goodfellow and company had? They basically asked this question: generator is weak, but can we not make it play a min-max game with a discriminator, which is strong, and use it to train a good generator? I'll repeat what I said. Discriminators were not doing well. Discriminators were very good. Generators were not so powerful. But what if we played a min-max game between a generator and a discriminator and literally use the discriminator effectively, in some sense, to teach or help the generator build up its muscles, right? By playing a min-max game. And that is the idea of generative adversarial networks. Questions, guys? I don't know how you guys feel. It's a very impressive and beautiful thought, isn't it? That you can train a generator to do this. And what is the effect? Remember, we saw that. How many of you remember this person does not exist? Right? All of you remember seeing that. They are those. It wasn't. I just said that it's a generative algorithm, not a variation autoencoder.
Take an example of my MNIST. The same situation. If I pass MNIST to that,
yeah,
I pass my MNIST as 9. How many times the cop is? So it is something like some letter that is called 9.
Yeah. So let's do that. MNIST dataset. So you have from 0 all the way to 9 digits. About what happens is you can either feed it a digit to the cop, the discriminator function, or you can go to the generator, Z sampled off noise, and feed it X prime. In the beginning, what the generator will, what the crook will generate will be just some noisy random pixels, isn't it? It will not look like any of the 10 digits from 0 to 9. So think about it this way. After a little bit of training, when will the generator begin to do well? When will its loss be low? When somehow it has figured out the distribution of this data. So suppose in some space, the distribution of this data is whatever it is, probability distribution. Right? So it has figured out that these are legitimate shapes. 0 to 9 are legit shapes. Don't generate some weird thing. Right? So for example, don't generate like this. This is not a good idea. Right? Instead, this is a good idea.
But that it's no control, right? Even the I was looking for evidence, but there's a house may come something.
Yeah. So the whole point is that as the generator departs, see what you're happening. So think about it this way. The generator generates something. It gets a big loss. It says, oh, right. And then changes. And it keeps on changing till it begins to. So I want to show this to you guys in action. Do you want to see it in action? The generator and the discriminator playing an adversarial game. Let's see it in action, guys. By the way, I don't know, guys, first time you encounter, well, today is 2024 and generatives are going strong. But when this came out, you can imagine that this was quite a revolution in AI. That you could use a simple min-max idea to play an adversarial game to come up with a powerful generator. And I would like to now show you how well. And so, guys, much water has flown down the river. GANs have become an entire field of AI. There are tons of research papers, tons of advancements, and tons of things. So, since today we are in an introductory course, I would like to, and trust me, when you come to the boot camps with me, if you stay here long enough, we'll make a cop and crook out of you. So let's play this game. Playing with GANs.
Ask a quick question, Paul. So is this a min-max game only for the training, and do we need?
Yeah, after the training is done. Very
good.
good question, Gopal. I got your question. Thank you for asking that. And sorry to interrupt you. Yes, once you have trained the GAN, the generator, do you need the cop anymore? No, right? Because the generator, that crook, can go on producing counterfeits, and now you can get rich. Right? So you throw away the discriminator. The cop was needed just to make a smart crook, isn't it? Because once a crook is trained, you have an infinite supply of counterfeits. Right? You are ready to buy that island finally. Okay, I'm joking. So let me frame what do you see on the screen? Let me frame it for you guys. Let's say that the real data distribution. You realize that we are talking about real data distribution. So look at this data distribution. Data is along a line, right? But does the generator know? The generator doesn't know, right? Does the discriminator know? Discriminator also doesn't know. I'll play this in slow motion. Let's run this. See what happens, guys. So look at the step. Generator derives sample from noise. So you're giving it some noise here, right? What will the generator do? It will shape the noise into some imagination of data, what it thinks looks like a valid data point. Right? For it to be a valid data point, it basically better overlap with one of the green dots, isn't it? But it won't initially. So let's do that. And let me just stop here. See what is happening. This discriminator, the cop, is getting data from both the generator and the real. And so it has to only come up with one answer. Is it real or fake? Now look at the blue line. The cop is told the answer both ways. Hey, I gave you a fake, or I gave you a real. But what about the generator, the crook? The crook is only told that you got caught. Is never told what the real looked like. It just said you produced a fake and you got caught, or not. Make sense, guys? Or the cop is suspicious. That's all you come to know. Let's play it out. So generator derives sample from noise. Discriminator classifies fake samples only. Computes generator loss. 4. Computes gradient and updates the generator. So this is when a generated data goes through this. When real data goes through this at the top, generator derives sample from noise. Discriminator classifies sample. Computes discriminative loss. Computes discriminative gradients, updates it. So pretty much, do you see that both the processes are? Blue is the life cycle of the discriminator, the cop. Purple is the life cycle of the crook. Does it make sense, guys? Think the blue, think like a cop. Generator will give it, discriminator classifies a sample it whichever way, computes discriminator loss, the cop loss, computes discriminator gradient, updates the discriminator on gradients. So both ways it is going to do something. Let's go to another. So look, guys, this is epochs. Huh? I'm just giving you a frame. It's going in very slow motion directly, deliberately I did that. And do you notice that at this moment, both the generator and the discriminator are clueless. They haven't learned anything. Right? And I will just remove the slow motion part and let it learn faster and faster. Well, this one is going a bit slow. Let me take another one. So we'll start with that. Okay, let's start with this. Okay, I'll just pause it here. Look at this. Oh, I went too far. Let me reset. So keep looking at the epochs. I'll run it for a very slow number of epochs. Actually, let me run it in slow motion. First epoch. The first epoch was what? There was, it seems that fake data went in, isn't it? And there was a loss, and this thing is learning. Maybe it's all going too slow. Discriminator loss, it's learning. Now, generator loss. Now the generator learns, discriminator learns, generator learns. You see these things, guys, different parts are being highlighted here. So this is all in very slow motion. Let me speed it up a little bit. Oh, I think there's a bug in there's a little bit of a bug here. Let me refresh this page. Okay, let me refresh this. Okay, I will stop somewhere here. Let's look at this. Maybe I'll reset it. It went a bit too fast. Okay, I'll just stop here. See, let's look at it carefully. This is noise, right? It's a plane of noise, isn't it? It has transformed this plane. Initially, you notice that it was a Gaussian noise concentrated in the center. And what has the generator done? Generator is just a deformation engine, right? It deformed it into what? Into a shape like this. Look at this, how it deforms this. You literally see the action of the neural network as a deformation engine. When it comes to that shape, what does it believe? That is where data really lives. It may be right or wrong. In fact, it happens to be wrong. Do you notice that in the real space, it believes that all the fake data is here. I mean, this is the real picture of the data. It has it completely wrong, isn't it, guys? Now, let's look at the discriminator. What is the cop thinking? Cop is also pretty wrong. it is thinking that everything in the top left-hand corner is real. Everything in the bottom, everything after that is fake. Neither of the two are right. Would you agree, guys? Neither of the two are right. They are both playing an adversarial game. Now what happens? Let's stop here. At some point, you see the cop has changed its mind. It actually flipped it. It began to say, because it saw that fakes were moving to this part. So the cop is literally chasing the crook's understanding, right? If it says that a crook is placing most of the fakes here, it changes its mind and says that's where the fakes are, right? You remember that a little while ago it was here, right? And so it has said this region is fake, this region is real. Let's go a little bit more. Okay, let's see now what happens. Now, you see, generator is thinking this is a good idea. This is how reality must be. And so it has built this plane. Now, do you notice that actually the generator is doing rather not so good at this particular moment? What about the discriminator? If you look at, see, you notice that at this moment, the generator loss has gone up because it has really made a bad decision. It believes the real data is here, but actually it is the place where there is no real data in the middle. Real data is above it. Real data is to the right-hand side of it. Are you seeing that, guys? So it has actually made a bad decision to go sit in the middle. But what about the discriminator loss? Do you notice that discriminator is beginning to smile? Is beginning to say, I got you, right? So we'll play this game a little bit more. Let's look at this. Now, well, I suppose I can't rewind it, but did you notice that it initially went to the upper blob, this blob, and it put it there. And from there, it has started spreading it out. So now what happens? Look at that. The generator loss is again, now, it's still pretty bad. It is making data points all over the place, right? But it is at least not sharply rising. What about discriminator loss? Discriminator is now beginning to get confused. Its loss is increasing. The cop is beginning to get confused. Do you see that, guys? And now let's play this game a few more epochs and observe what it is doing now. You notice that the generator is putting all the data along this banana shape. And in a way, the cop has figured that part out. Right? What it is now, the problem with the cop is it is relying on or figuring out what the generator, the crook is doing. But in this sense, it's also getting confused because, see, regions where there is genuine data, it's not able to figure out. Right? And so we'll let this game play itself out. You see how their understandings are continually changing? Look at this. At this moment, what do you think? Do you notice that the generator is beginning to do well now, right? It's putting all of its points here. At least it's putting the points close to where the real points are. It's fakes close to that. And you can see at that particular moment, the generative loss and the discriminant loss, they're beginning to even out, right? Let's play it a bit more. And now do you see that, look at that, for this, do you see that the discriminant is coming up with some very bizarre theories about real and fake? Isn't it, guys? When you look at the picture that the discriminator is drawn, it has a very poor understanding of reals and fakes.
So the
Right?
discriminator was never told this is real.
No, only when it makes a mistake, it was told how much mistake you made. Remember, loss just tells you how much mistake you made. Nah. And from that, it is doing a gradient descent. And
You would think that it would figure out given that the loss of the
yeah, it does. And the whole question is, who is stronger? Like, is the discriminator stronger or the this thing is stronger? But do you observe something very interesting, guys? This thing, the generator has figured out at least one band where it seems to which really overlaps with the real data, isn't it? So what is it doing? See, in AI we speak about exploitation versus exploration. Do you notice that in the beginning the generator was exploring the space for opportunities, but now it is not exploring that much. It is pretty much beginning to exploit areas that it has found are good, right? And let's play it out a few more. I hope you guys are not finding it too tedious that I'm running it so slow.
Yeah. Actually, like the activity is very high for the generator because the metrics on the right side,
yeah,
the gradient for discriminator is flattened out a little bit.
Yeah. So I'll just pause here. Look at this, guys. Look at the shape that the generator has come up with, the samples. Is it beginning to look like the real one? Isn't it? And isn't it magical? The generator never really saw the real. All it was told is how wrong it was when it generated something. And from that, it is beginning to get pretty close now. And observe also what is happening to the KL divergence, guys. KL divergence measures what? The gap between the two distributions, right? Data, what the Crook's imagination, generator's imagination of the real data versus the actual real data, distribution of the real data, right? They're beginning to, the divergence is decreasing gradually. But do you notice that now the generator is not making drastic changes, is it? Is it making drastic changes, guys? No more, right? And do you notice that the loss of the two are beginning to converge, right? The generator is becoming pretty good at And if you look at these two pictures, the samples and the real, do you realize how very similar the two look? Do they look similar?
Basic question, like how discriminator knows, hey, this is wrong.
No. See, it's simple, no? Who's the code that is feeding in the answer knows the answer. Supervised learning means what? I give you X. I ask you, is it real or fake? Probability of real. Suppose you say probability of real is 80%. But no, listen to me. Probability of real is 80%. But you know the answer, right? You are neither the generator nor the discriminator. You are the code. You know the answer. Yeah. So you can then say, hey, I will take the log of your probability. Why? Because I knew that this was real. Discriminator is not told, but discriminator is told you were wrong by this much. So if the discriminator says 80% and it is told that, yeah, you were somewhat wrong, the discriminator may choose to infer that, yeah, I got it right, right?
But I'm assuming that the real, because of the real already playing with the usually start playing with the real data based on that.
No. It is randomly. The discriminator is being randomly once given a real, once given a fake. It's never given in a sequential order. Because then the discriminator will have an edge. It will immediately figure out the distribution of the real, and the generator will stand no chance. So guys, look at it, how uncannily similar, how good the generator has become. So what are the uses for this, guys? Let's pause it and think, and I'll run it for another one. And while we are doing that, I will let you think about it. observe how it is. Yeah, look at it. The generator is totally off, isn't it? At this moment, it has some weird hypothesis. I'll reset it and start again. Look at this. Generator's hypothesis of the data manifold is completely wrong, right? And in the beginning, the copy is doing really well. Anyway, so as this thing runs out and you can look at it, you see how imaginative and interesting hypothesis the generator is making about what is real. It has never seen the real. It's just making hypothesis after hypothesis, and through a process of gradient descent, see how uncannily close it comes to the reality in barely 700-800 epochs. Like we are still doing, we are not even reached 1,000 epochs. Looks true? Looks fun, right? And here's the best part. If you look at the details, discriminator is actually 2 hidden layers, 9 neurons. Generator is only 1 hidden layer, 10 neurons, right? What happens if I run the game with, let's say, more powerful network? Let me do it 20 neurons. Let's give it 2 or 3 layers. Can I run this game again and see what happens now? Right? See what happens. I'll make the learning rates more or less the same. 0.03. Make both of them into atoms. This is by now should make sense to you. These are your optimizers. What happened? Discriminator is winning hands down. Isn't it? I don't know why. This is, let me take a slightly different value. It is pinching all the fakes here. It's getting it really wrong. Let me try it again. Yeah. And it has gotten into a situation. Right? Now what I'll do is I'll increase the learning rate. And see, guys, you have to play with this, more or less. Anyway, it will catch up. Gradually, it will begin to catch up, and I'll let it catch up. So, guys, what are the practical uses of this? When you have a generator that learns the distribution of the original data, what can you do? If nothing else, you can use it as a data generator. In fact, a data generation is one of the best use cases for GANs. You saw that, right? It could generate, for example, data comes in all kinds. When we went to this, now, by the way, if you look carefully at the bottom, it says it's a GAN. It's a kind of GAN that produced it, and how utterly realistic it looks. And now you have an idea how these GANs work.
Asif,
Yeah, go ahead.
are GANs more lightweight like CNNs than transformers?
GANs are made up of CNNs. See, okay, that question, let me answer that question. See, guys, I said generator and discriminator. I didn't tell you inside what is the neural architecture. Isn't it, guys? I didn't say that. So what are the 2 architectures you have learned? No, at this moment, feed-forward networks, dense layers, and convolutional layers. You can put, and remember, you're taking noise and creating a high-dimensional data out of it. So it is actually deconvolution. Deconvolution. Remember the decoder part of it, decoding noise into something meaningful. So people, I'll put D there. It's a convolutional network, the transpose of it. You do that, or you can do it as a feed-forward Or when you become aware of attentions, you can do it with transforms. Right? And these days, there's a whole lot of research mixing things up and doing things, etc. Now, I realize that we're more or less getting out of time. Guys, I'll request you to play. This is the homework I'm giving you. Play with that lab. And I want to give 15 minutes to going over the original paper in a moment. One thing I'll tell you, see this space, when you sample off this space, soon you figure out that in this space, if I pick this point, sample from this region, let's say, this produces people with, let's say, black hair. I'm taking an example. This produces people with, let's say, blonde. And this produces people with, let's say, auburn. And so what can you do? This gives you the axis along which you can move to create degrees or gradually decide how to move. This is, by the way, this is not exactly, it's an oversimplified version of things. But do you see you can do that? Does it make sense, guys? No, it doesn't. There's more to it. Actually, the whole GAN theory is a bit elaborate, gets quite complicated. But in this introductory class, I'm introducing you to every neural architecture. I hope you found this introduction fun and mostly clear. So how many of you feel you got some sense of what the architecture is? If you felt you got the main idea, raise your hand. Okay, good.
So
Yeah.
the question, this happens during the training of the generative model, right?
That is true.
Once it is trained, then this process doesn't need to be.
No. Once you have trained the model, what do you discover? You discover that when you sample off, so suppose you're sampling off points from a two-dimensional plane. And if you figured out that this is where I get black-haired people and this is where I get auburn-haired people, yeah, you can pick your degrees. See, I've oversimplified it a little bit, but I'm giving you the basic idea that you can do vector arithmetic there in the generative space.
Okay. And then just from a training perspective, it seems very computationally expensive, at least intuition-wise, because you are kind of just starting a complete randomness.
Yes. Of course, these things are only possible in this world where you have access to that computational power. GANs take time to train. Also, one of the issues with GANs has been traditionally, like I said, right, originally there was a very preliminary proof of concept. GANs are very notoriously hard to make them stable. Right? Like you're not careful, the discriminator will become too powerful or something like that will happen. So you have to find the right balance to train the generator well, right? And still keep diversity in what it produces. And so there are all these theories of cycle GAN, this GAN, that GAN. It's a whole world of research, which I refer you to in this resources when you go to. Oh, now I hope this picture makes sense. Nobody is amused. Okay.
So who's the group problem?
Yeah. So
You can go ahead, Krishna.
Asif, so we can achieve the similar thing. We can achieve the similar thing with the variational autoencoders, because they're also like I can pick a point and then I can generate whatever I need to, because like it is going to be, it is converged at
True, Ganges, you're right. So here's the reality. See, as an idea, GAN is a powerful architecture. What it led to is a horse race. I mean, it led to its own adversarial game between the variational encoder people, researchers, and the GAN researchers, both trying to outdo the other, because both are generative architectures. And sometimes the VAE would come up with one more clever trick to make it really good. And then the GAN guys would come up with something to make theirs really good. So there is a min-max game happening right there. Two-player game happening between these two communities. End result is both communities have become very rich. Variationals have become, this autoencoder based generative models have become very good, and GANs have become very good. And both are very active areas of research.
So, one question is that we said that the inputs when we start training based on randomness noise. And also I saw you said that both the deconvolution and feed forward. So we train the model so that we come to a latent space which has a noise sample and then we feed it.
No. What happens is that, where is that thing gone? You are basically saying, I'll give you noise. Learn to shape it in such a way, from the noise manufacture a real point. Like, in other words, it's like giving clay. If I just gave you clay, you have to be a really good maker of statue. In your mind, you must have a conception. Let's say you're making a statue of a god. You must have a mental picture of the god to be able to shape clay into that god, isn't it? Generator is exactly that. During the training process, generator basically says, give me anything. I have a mental picture of creating a realistic looking object out of it. Make sense? That is, when you look at it, for the longest time, it looks unbelievable that this works, isn't it? Like, generator is starting with nothing, with noise, and it is able to shape it beautifully into something realistic. It's like you get clay and you mold it into something realistic. Isn't that amazing? Right? That is why when GANs came out, people were just completely stunned. They were just stunned that this could be done.
To understand the behind the scene, DALI, anything like
One second. I'll come to your question. Guys, we weren't paying attention to this, but do you notice that this and this are beginning to look very close to each other now? Right? Anyway, your question is?
Reality, like now the picture generation. So when we are typing a text, so the text there is no data in that. From where the data is forming that?
I don't know. What is the text?
Creating any image generation process like DALI or.
Yeah, you give it a text. So, no, those are different algorithms. We'll come to that. It is not done through GAN. No. DALI is not based on GAN. But see, we are in the generative world. I've just shown you 2 of the little animals in the zoo. There are many more interesting animals in the zoo, exotic animals. Right? So DALI architecture, are you there in the Sunday boot camp? Okay. I'm just about to cover diffusion models in DALI. Yeah. So let's keep it for you. You're going to come to the boot camp. So you'll learn it. See, guys, at this moment, I'm giving you a tour of the zoo in which I'm just introducing to you, here's the giraffe, and here's the zebra, and here's a hippopotamus, right? I'm just introducing you to the major architectures. In due course of time, all of this will become familiar territory. And I have not taken you down to the code level at this moment, partly because of a lack of time. And there's frankly so much territory to cover. But you'll see that after the course ends, ironically, I'll be dumping a lot of code onto the course portal with notebooks and use that as a bridge to get ready for the boot camp. Right? Those examples, use it to get ready for the boot camp. So see, guys, by the time you reach this stage, look at the discriminator. Do you realize that the discriminator is more or less lost? It has this wide region of white in which it doesn't know whether it's real or fake. But yet, it has figured out that in the center it's fake and outside is fake, right? And the data is hiding. So what the generator has done is it has confused the cop. A large part of the real data territory, it has created imitations there, right? And so the cop is confused. Guys, is that visible to you?
Yeah.
Yeah, that is GAN, guys. That is this beautiful, beautiful architecture, a neural architecture of GAN.
So once the model is trained, let's say if you want to use this besides data generation phase, but
Yeah,
how would you, what kind of input would you give to the model so it index?
random noise. You don't give it any input. You say, give me, like, look at this. Did you give it any input for it to generate one more phase?
No, there is no prompt or
Nothing at all. With GANs, you just say, go generate. Now, there is a little bit of there, but if you insert a noise, like I told you, if you deliberately choose what noise vector to give, then you may end up with shapes that are specific, right? That is style GAN, cyclic GAN, and so on and so forth. But at this moment, it's a little bit slightly advanced topic. But for now, just imagine that you're sampling off noise and producing realities. Now, guys, that is not the end of GAN. I want to show you something today, end with something magical. Can I have another just 10 minutes? If you look at playing with GAN, there is something called neural style transfer. That is so amazing when it came out. It was just unbelievable that you could do it. I'll just take it to you. There are lots of websites that do it. So, Van Gogh is, let's take an artist, Van Gogh. Van Gogh is no more, right? Yeah. But what if you could resurrect Van Gogh and say, here is a photo, now redo it in your style. That would be amazing, isn't it? And that is literally, oh, look at this. Wow. Here is a Van Gogh style. You give it a picture, you give it a real Van Gogh image, and you say, now re-render this original picture. So if you look at the original picture, guys, this is a picture of a girl, young girl, right? Isn't it, guys? Not particularly remarkable, right? Just a pretty picture, a very nice looking picture. But then this is a famous Van Gogh painting on the right-hand side. And then you resurrect Van Gogh and say, go paint this girl. And what do you get? How many of you can look at it and say, well, this is literally Van Gogh style, right? And this is really best appreciated if you look at it in a large, look carefully at the details. And if you're familiar with Van Gogh's style, do you see how realistically it imitates Van Gogh style? Guys, you know about the artist Van Gogh, right?
Yeah.
Starry Nights and all of that, right? So you could do a lot of things. So we are in the world of generative art now, using GANs, using this. So neural style transfer is one of the big achievements of GANs. It started with GANs. Now people are bringing all sorts of other diffusion models, etc., into it. But now you can write poetry in the style of your favorite poet, whether it is Ghalib or Shakespeare, or it is Tirukural. You can take whatever and say, write it, the whole thing as a Tirukural. And your AI models will do it for you. Right? Write it as a haiku, as a sonnet, it will do it for you. Right? Write it as, paint it like this, it will do it for you. It is both exhilarating and frightening, isn't it? You have a near collapse of reality. It becomes harder and harder to tell reality apart from creative.
Deep fake.
Deep fake, yes. Right? And well, that is it. But behind all of this, I hope you realize that there are these beautiful architectures and neural architectures that make it possible. All right, guys, that's all I have. By the way, neural style transfer, I give this to you as a homework, guys. Go play with neural style transfer. Can I request you to do that? There are lots of websites. Upload a picture of yours. Pick a favorite artist. Have your photo rendered in the style of the favorite artist. Right? In India, there was an artist, right, Ravinder Verma. Right? So take the picture of your family and have Ravinder Verma, right, paint it for you. Or I don't know, pick whatever your favorite artist is.
So that input to the model that started.
In the neural style transfer, it uses GAN. There's more to it, but it uses GAN internally to make it possible to do that. How it does that, we didn't get time to cover that paper. So what I did, guys, is it is a big topic, and I put a neural algorithm for artistic style. This is the research paper. And I put pretty much the original research paper here. So guys, look at this. You have a normal picture of buildings, right? And I believe this looks like Monet to me. Oh, does it look like Monet or does it look like Turner? I don't know. A photo, the painting, the styles is shown on the bottom of each panel. Okay. So do you see, guys, this same picture is rendered in Van Gogh style. Cubist, this looks like Cubist style to me. Oh, yeah, Vincent van Gogh. So yeah, here A is the original picture, the painting that is generative, B, the shipwreck of Turner. Yeah, I got Turner right. Okay.
This is the same technique used for like how this is the age when you go backward and forward that the aging. Age, like take a person,
Yep.
go from the how.
Yes,
the
yes,
person
yes.
was
The same
young or
techniques
the
you can
later
use.
on.
Absolutely. You can do that. So guys, yeah, so nice. I remember my Turner, Picasso, and so forth. Last one, I have no idea who it is. Vasily Kandinsky. But yeah. So with that, I'll stop.